nitrogen oxides and ozone measurement. It's built for this aircraft recently, so these are its maiden flights. And we're measuring 4 different things simultaneously every 1/10 of a second in the atmosphere, so about every 100 feet as the aircraft travels. The things we emit, including these things down here that we're measuring, drive ozone photochemistry in the atmosphere. So power plants, tailpipes of cars, your backyard barbecue, forest fires, make these nitrogen oxides. They're reactive, and they cook along in the sunlight in the atmosphere to make ozone as part of the ozone recipe. It's a pollutant, and it affects people's health, and it affects the viability of plants. And it's also a substantial greenhouse gas. And so it couples to both air quality and to climate. So this is how we try to look at our data. We flew up and down in this black trace. And the ozone has a vertical structure shown here in blue. And the nitrogen oxides we're measuring are shown here in red. And you can see that very similarly, as we're heading south, going up and down, you kind of get this decrease as you get closer to the equator. And all of a sudden, the ozone you see here and the ozone you see here is missing at the highest altitudes, very close to the equator. The contrast between north and south is going to tell us a lot about how the large sources in the north of human pollution affect the global atmosphere differently in the south with fewer sources, and different hemispheres will have different seasons as well. If you see this really boring stretch down here, down south, close to the equator in southern hemispheric air, and that little line looks really flat, but if you zoom in, one of the many things we're going to hope to be able to do with these data is to say, how fast does this gas, this greenhouse gas, this pollutant gas, ozone, stick to the ocean surface and go away from the atmosphere? And that's a really key thing to get right in the global climate and global chemistry models.